Hey everyone, geophysicist Stefan Burns here. Breaking news, a new rogue object has been found hurtling through our solar system directly in between interstellar object 3I Atlas and Earth.
Within the span of a single week, two rare and enigmatic objects, 3I Atlas and C 2025 V1, swept toward the Sun on sharply different trajectories, each carrying signatures that defy easy categorization. One is undeniably interstellar, the other nearly so, and both arrived with a timing that feels too precise to ignore. The coincidence alone has triggered a surge of scientific attention, not because the connection is obvious, but because the odds of such an overlap are astonishingly slim.
Well, on November 2nd, Gennady Borisov, an amateur astronomer, discovered an object near the Sun that is actually barely bound to the Sun, so it's almost interstellar, but most likely it came from the outskirts of the solar system, the Oort cloud. And that was surprising because that's around the time, the same week, that another interstellar object passed close to the Sun, 3I Atlas. That one we are confident is interstellar because it was moving at 60 kilometers per second, very high speed, 600 times larger than the fastest car we have on Earth.
Appeared first as a faint, plunging object in early November, moving on a path so steep it cuts almost perpendicularly through the plane of the solar system. With both objects descending toward the Sun at the same moment, the natural question emerged: could their arrivals be more than coincidence? Orbital calculations strongly argue against a shared origin, yet the unfolding observations from 3I Atlas, its unexpected structural coherence, its powerful jets, its puzzling sunward features have complicated the narrative. Even if the two objects never crossed paths in space, their simultaneous appearance has forced astronomers to confront a deeper mystery. Why did two of the strangest visitors in recent memory arrive together? And what exactly are we witnessing as they evolve under the intense scrutiny of the Sun? C 2025 V1 entered the scene when it was discovered by Gennady Borisov, the amateur astronomer who previously identified 2I Borisov. Its motion immediately raised eyebrows. It carried just enough hyperbolic excess velocity to tip outward from a typical long-period comet, but remained close enough to the boundary that minor perturbations or non-gravitational forces could nudge it either way. The shape of its orbit, when projected back to large distances, suggested an origin in the far outer reservoirs of the solar system, rather than a journey between stars. Yet its steep inclination, more than a right angle relative to the ecliptic, placed it on a path that cuts deeply across the solar system's usual geometry. There was no natural reason for its arrival to align with that of 3I Atlas. The two objects occupy orbital planes so differently tilted that they form something like a cosmic cross, paths that never intersect and never bring the two bodies meaningfully close. And yet, there they were, almost side by side in the inner system, separated by timing, only days apart. This coincidence was not lost on astronomers, who routinely deal with statistical likelihoods. Even when the mechanics are understood, the simple appearance of two highly unusual bodies in the same solar week forces further scrutiny. It is rare enough to see a single object traveling on a path flirting with interstellar velocity. To see two at once, one confirmed as interstellar and the other masquerading as nearly so, invites deeper investigation. The dynamical analysis is straightforward. When the orbits of 3I Atlas and C 2025 V1 are extrapolated back in time using only gravitational interactions, they never approach each other. Their closest orbital separation is tens of millions of kilometers, their physical separation even greater. Nothing in their gravitational history suggests a shared origin or even a passing encounter. Even if one imagines a larger parent approaching the solar system and breaking apart, the angles make that scenario impossible under natural conditions. For a debris fragment to arrive on the orbit, now assigned to C 2025 V1, it would have required a dramatic, precisely oriented impulse, something natural fragmentation cannot produce. especially at interstellar speeds. The timing alone, however, has kept attention fixed on the pair. That attention intensified as new images of 3I Atlas arrived from observatories around the world. Instead of emerging from its close solar approach in tatters, as countless comets have before, the object remained intact, a single body with a clearly defined nucleus. But it was the behavior of its surrounding dust and gas that seized the narrative. High-resolution imaging revealed a stunning elongation pointing toward the sun, a sunward antitail, a direction rarely associated with typical cometary behavior. Some comets exhibit antitails due to perspective effects and the dynamics of dust sheets. But the geometry here differed. The alignment was too direct, the structure too consistent, and the object's overall behavior too unusual to dismiss as a simple optical effect. Jets streaming from the nucleus stretched hundreds of thousands to millions of kilometers both toward and away from the sun. These jets were not minor flares or intermittent puffs. They formed imposing structures visible even through moderate telescopes, indicating substantial mass loss. The natural explanation is sublimation. Sunlight heats surface volatiles, which vaporize and expel dust. But this comes with an energy cost, and the scale of the observed jets demands an enormous amount of absorbing surface area, vastly larger than its measured size. Imaging constraints place the nucleus at no more than a few kilometers in diameter, yet to expel the billions of tons of material implied by the jet lengths, the surface would need to intercept many orders of magnitude more solar energy than a body of that size can realistically absorb. This discrepancy is not cosmetic. It strikes at the heart of the natural model. If the jets are produced by sunlight evaporating surface ices, the energy must come from the sun, and the surface must be large enough to absorb it. If the surface is too small, the sublimation cannot occur at the necessary rate. The behavior of 3I Atlas, as observed, requires either an unexpectedly high volatile content combined with favorable thermal properties or an alternative mechanism of ejection. The presence of a stable, pronounced sunward jet complicates the picture further. Radiation pressure should push dust and gas away from the sun. But here, a clearly defined structure extends toward the sun, maintaining coherence even as the object moves through varying solar conditions. Post-perihelion survival itself is noteworthy. Many long-period comets, especially small ones, do not endure close solar approaches. They fragment, outburst unpredictably, or disintegrate entirely. 3I Atlas remained whole, exhibiting none of the chaotic breakup signatures expected of small, volatile-rich bodies heated to extreme temperatures. Instead, it produced jets of a scale large enough to demand explanation without sacrificing its structural integrity. C2025 V1, meanwhile, appears far more conventional in its physical behavior, though its orbit remains unusual. As additional astrometric data accumulate, its trajectory becomes increasingly consistent with an Oort cloud origin. When projected beyond the region influenced by planetary perturbations, the orbit likely falls below the hyperbolic threshold. Its slight excess appears attributable to either measurement uncertainties or non-gravitational forces typical for active comets. But none of this accounts for the coincidence of its timing. If anything, the contrast between its relatively normal cometary behavior and the anomalous dynamics of 3I Atlas has only heightened interest. This is not a case of two bizarre objects arriving together, but of one nearly interstellar traveler accompanying an unquestionably interstellar one acting normally, the other defying expectations. As if this were not enough, a remarkably frustrating development has emerged. Key data captured by a Mars-orbiting spacecraft remain inaccessible due to procedural restrictions triggered by a government shutdown. These images, taken when 3I Atlas passed near Mars, represent some of the highest resolution observations available. With a resolution fine enough to detect structural and morphological features on the object's surface or in its jets, the dataset could provide clarity on several open questions. Yet the data remain locked away, unavailable to the scientific community, even as researchers urgently tried to model and track the object's evolving behavior. This delay has impeded the ability to adjust telescope schedules, refine orbital solutions, and test hypotheses about the nature of the jets. Few moments in recent astronomical research have contained such a stark disconnect between available data and scientific need. Against this backdrop, a larger movement within astronomy and aerospace research is gaining momentum, one dedicated to systematically studying unidentified aerial and spaceborne phenomena using rigorous instrument-based methods. New observatories have been deployed with specialized cameras, infrared sensors, and machine learning software designed to categorize millions of moving objects per year. The goal is not to chase anomalies for their own sake, but to develop a comprehensive catalog of everything that crosses Earth's skies or passes through the inner solar system. Within such a framework, objects like 3I Atlas become especially valuable. Their behavior tests the limits of models used to classify known natural phenomena. They force researchers to confront outliers that do not fit neatly within training datasets. This context is essential because the characterization of 3I Atlas as an anomaly rests not merely on its origin, but on its observed behavior. If the jets are powered by sublimation, then the mass flow, energy absorption, and jet geometry must fall within known cometary parameters. If they exceed those parameters, alternate explanations must be considered. The upcoming close-approach observations will be crucial. Telescopes will measure jet velocities with unprecedented precision. Natural sublimation is constrained by the thermal velocity of outgassing molecules, typically a few hundred meters per second at most. Technological ejecta, by contrast, can produce velocities several times higher. The difference is measurable. A high jet velocity would indicate a mechanism far more energetic than sunlight vaporizing ice.
Yet, even if the jets turn out to be purely natural, the object remains unusual in other respects. Its survival through perihelion, its persistent sunward feature, and the mismatch between jet scale and energy budget collectively mark it as an outlier within the known population of active bodies. It may represent an extreme example of a natural cometary process not yet encountered in detail, or it may challenge the boundaries of what natural can encompass. Scientists are not accustomed to confronting such questions in live time, especially with interstellar visitors. As for C-2025 V1, its role in this unfolding narrative may ultimately be to highlight the strangeness of 3I Atlas by contrast. A normal, if unusually inclined Oort cloud object arriving at a moment of heightened attention creates a backdrop against which the anomalies stand out. It serves as a reminder that not every unusual orbit implies an unusual nature. Yet its timing is undeniably curious. Even if the two objects are entirely unrelated, their paired appearance will likely be remembered as a turning point, a moment when multiple lines of inquiry converged on the inner solar system at once, compelling astronomers to reconsider assumptions about frequency, coincidence, and the distribution of unusual bodies entering our observational reach. As the year draws toward its end, the anticipation surrounding the next phase of observations grows. 3I Atlas will soon approach a distance that allows the world's largest telescopes to probe its jets with the greatest sensitivity yet. Spectrographs will measure composition, interferometry will map structures, and photometry will track changes in brightness and activity. Each piece of data will narrow the range of possibilities. If the jets are slow and consistent with volatile sublimation, the object will remain a peculiar but natural member of the interstellar population. If the jets exceed known sublimation velocities or exhibit directional control inconsistent with natural processes, a far deeper mystery will emerge. Regardless of the outcome, the question of whether 3I Atlas and C-2025 V1 are connected has already served its purpose. It has sharpened attention, accelerated modeling efforts, and directed a global network of observers toward two visitors whose presence demands explanation.